record and start that running. Okay, so I'm going to start with like the last, I think the last thing in my abstract I said I would discuss applications in quantum mechanics. I'm going to start discussing the applications in quantum mechanics. I could just say, well, we assume we have a variety defined by 1,000,000 equations and 100 variables, but where does that come from? Why do we care? So I'm going to start with that, and then probably in the second half of the lecture, move on to the algorithm proper that I'm working on. So yeah, Michael was just asking, we came in, what is the steady state Schrödinger's equation? This Hamiltonian operator. It's basically like Newton's second law, F equals ma for quantum mechanical systems. And if we just assume there is no time dependence, then we get the time-independent Schrödinger equation. So we just assume we assume the probability distributions in both position and momentum are constant with time, and that is a steady state in quantum mechanics. The atom just, quote unquote, sitting there. You have just a, just a bare, imaginary universe, just like a bare atom, just sitting there in the middle of it, just, not doing anything, not interacting, not moving. It's not like the proton and the electron don't just assume like fixed positions, because in quantum mechanics there is no zero energy ground state. So there are steady states that where you have a probability distribution. You look around, you might find the electron here or there, some other place, but it is steady in the sense that there is no time dependence in the probability of either the position or the momentum.
Well, another way to say it is that you could make it time dependent. It's psi of t equals e to the I e
yes.
t times this thing.
That's right.
Or with a proper sign.
Although I've kind of gone the other way. I've already taken that out.
Right.
It would be
and we're
here
just ignoring
with
that.
is. Yeah, we're just taking that out. We're assuming that it's just constant. What we have is a complex valued wave function. It's complex because it encodes both the probability, the position, and the momentum. So the position is the probability of the position in some location is proportional to the magnitude, the complex magnitude of the thing. And then if you take the Fourier transform, that gives you the probability distribution of the momentum. So that's why it's complex, two-dimensional. It's both probability, F equals ma. When you specify a system of classical particles, you need to specify their positions and their momentums. In this case, in the probability, the probability of quantum mechanics, we specify a probability distribution of both the position and the momentum, and it all gets wrapped together in this complex valued wave function that we're interested in solving for. E is the energy of the state, which is a real number. 0 is all the particles at rest at infinity. And if you think they start accelerating in, they would just kind of like zip past each other and keep going. So a bound state is going to have negative energy. So you have to remove energy in order to get like a proton and an electron like locked together in an atomic orbital. Make sense?
I'm sorry, it's appropriate you're wearing the right garb and in the right place to be arguing this. But it seemed kind of, in the beginning, can we back up a little bit?
I'm afraid this is...
You have one particle, you have a finite, we assume we have a finite number of particles in three-dimensional space, in four, H hat.
It doesn't matter.
So in one sense I'm going to say, yeah, it doesn't matter. On the other hand, I say, yes, all the cases I'm interested in, it's a finite number of particles, three-dimensional space.
The wave function is an L2 of R3n.
Yes, 3n because it's a function of the position of all the particles simultaneously. So you have the nucleus at the origin and two electrons orbiting around it, helium. Then...
Is it 3n or 6n?
It'd be 6. Well, it'd be 3n. N in this case would be 2. 2 electrons would be 6-dimensional.
You take the Fourier transform, you'll have another 3n.
Uh-huh.
I mean, you have position and momentum.
No. You just need position. And then if you take the Fourier transform, you're converting to the momentum representation.
Okay. And can you explain what Hamiltonian operator means if we're going to invoke the physics? Because I don't really know.
It's just some jibber jabber that
I guess
used for quantum
Hamilton,
mechanics.
well, yeah, actually Hamilton was prior to quantum mechanics. He proposed like an alternate formulation of Newton's laws of mechanics, both Hamilton and Lagrange.
Yes.
And it's ultimately the Hamiltonian approach, which is more energy-based and force-based, that has turned out to be the...
It's kind of an analog with the
Yeah.
classical energy, but it ain't the same thing.
Yeah.
Okay.
Okay, so here's the simplest example.
And there it is.
Hydrogen. We have one proton at the origin and an electron, moving around it. So this is what our Hamiltonian looks like in this particular case. The function is in 3 space, x, y, z, or you could pick spherical coordinates, sometimes more convenient. You have -1/2 the Laplacian, I think that's called, squared. It's, like the gradient or the gradient of the divergence, the gradient of the divergence, I think. Second derivative, if it's x, if it's x, y, z coordinates, it's second derivative in x squared plus second derivative x plus second derivative y plus second derivative in z.
It's usually written the opposite way, isn't it? With a delta, not an upside down delta?
No. Yes.
I can't remember.
The Laplacian is, but this is del dot del, which is the Laplacian.
Yeah.
Okay.
Yeah.
Upside down, it's the Laplacian. I mean, del dot del is equal to Laplacian.
Okay, so capital delta already is of order 2. It's a second derivative. So this would be capital delta for us.
Yes.
Okay.
Yep. And then this is that's what gives you the kinetic energy, and then this is the potential energy term, and it's just radial dependence on it's inverse square law, but the potential energy instead of the force, so it's 1 over r and not 1 over r squared. Normally, a lot of times when you see this thing, like on the internet or something, it's got all kinds of, physical constants, but constants tagged the one in front of it. This is, you drop all the physical constants. It's just the most convenient form to work with mathematically. We call them atomic units, where the Schrödinger equation is dimensionless. Like electron mass is 1, elementary charge is 1, and the Planck constant is 1, the Coulomb force constant is 1. A little bit of a weird system of units. Speed of light is about 137 in this system of units. The energy is, it's called in Hartrees. The advantage is it's just a pure math problem. We just don't have to worry about, convert, symbols or anything like that. We just treat it as a pure math, just trying to solve I wouldn't say it's a PDE, but it's more of an operator where we have an eigenvalue, eigenvector problem. So until we know what the eigenvalues are, we don't have a differential equation proper. It's really, it's a eigenvalue, eigenvector problem. And this is our operator, it's a differential operator. Bunch of stuff being neglected in that very simple Hamiltonian. No relativity, no magnetic effects. All of these things have, both the electron and the proton have magnetic moments, and the things orbiting around, so that creates a magnetic effect. Spin is a funny quantum mechanical thing that I don't understand, but these effects are neglected. Schrödinger's equation in general can handle that, and it's really just the complexity of the Hamiltonian that you construct that's just how simple or complex it is. This is a pretty simple Hamiltonian. It models hydrogen up to effects that can be measured. So okay, how do we solve hydrogen? Let's try a separation of variables. Let's assume that the solution separates. We plug in, and it turns out that it does separate. We get a radial term that are Laguerre polynomials, and then the angular term, they're spherical harmonics, and these are the first few solutions in atomic units. The energy's in Hartrees. The ground state energy is -1/2, and then as the first shell, and in the second shell, the energy is -1/8, and then -1/18. It goes as 1/2n squared, where n is the shell. And as you can see, as you go up, you get more and more complicated solutions.
Those are solutions to what now?
Those are solutions to the Schrodinger equation.
I see.
That Hamiltonian times the function equals energy times the function. This Hamiltonian, -1/2 Laplacian minus 1/r, operated on the function. And then if these are your lowest eigenvalues here, you put them in on the right-hand side, and then these are some of the functions that will solve your PDE. And then the differences between them give you certainly for hydrogen, and it was for helium too. It's not nearly so simple for more complicated atoms. That the differences between you give you the energies that you then see in the spectral lines of hydrogen, for example. Okay, so we've solved hydrogen, and now it's on helium for that obvious next choice, right? So now it's 1 proton at the origin, 2 electrons, so it's in 6-dimensional space. X, Y, Z for each electron. And this is what we get for our Hamiltonian. Now we have 2 kinetic energy terms, 1 Laplacian for each of the electrons. Partial with respect to x1, y1, z1, the other one's x2, y2, z2. And then our potential energy, we have our attractive potential to the nucleus, and also a repulsion term because the electrons repel each other. And this actually is what really starts mathematically is causing us some grief, because the equation doesn't separate now because there's repulsion. You have this, it's not just simply spherically symmetrical. Okay, so can't separate it like hydrogen. We don't have any known closed form solutions. However, any solution will let us at least put an upper bound on the energy, and this idea turns out to be fundamental to probably the last century of solution attempts for helium, or all of them really, and that is simply that if we compute the expectation value of just given any wave function that does not have to be an eigenfunction. It really just doesn't assume hardly anything about it. If you compute this integral, the norm, of course, in the denominator, and then the expectation value of the Hamiltonian in the numerator, it's going to be greater than or equal to the zero state energy. And in one sense, the proof is fairly simple. That if we just expand these things out in terms of a basis of eigenfunctions, and we have a ground state energy, we just collect terms, and no matter what the weighing parameters lambda are, that this function is expanded out in terms of weighing functions of these various eigenfunctions. No matter what the lambdas are, it's going to be greater than or equal to the lowest energy, the ground state energy. What makes this work is that H, the Hamiltonian, is lower bounded, compact, and self-adjoint. The compactness and self-adjointness, that's what gets you that you can find a set of eigenfunctions that are they are a complete basis for the function space the thing is operating. I mean, that's kind of a neat trick. You just pick a bunch of eigenfunctions. Why would they form a basis for your domain? It's the compact self-adjointness of the operator that makes it possible that you can select a basis for the domain that is formed of eigenfunctions of your operator, and then the lower boundedness is what makes it actually is an E0. I mean, those eigen values could go -1, -2, -3, -4, on forever. It doesn't necessarily stop that from happening. So those are the major conditions, and you can prove all of this that the Hamiltonian satisfies these conditions. It's a lower bounded, compact self-adjoint operator, and that's what makes this trick work. And it means that no matter how bad your guess is, if you compute that integral, the expectation value of the Hamiltonian, you get a value that is no lower than your lowest, your ground state energy. So you can put at least an upper bound on what your ground state energy is. And you can take this basic idea and expand it out a little bit, and you can also put an upper bound on it as well. So you can just kind of take almost whatever guess you want and bracket your ground state energy between an upper bound and a lower bound. And then, hopefully, if you made a pretty good guess, you get a pretty close bracket. And people started doing this, Hyrias back in the 1920s. He was the first one to really, do this successfully. This is the Hyrias expansion, exponential of the sum of the two radii, and then you have the sum of the two radii, the difference of the two radii, and the distance between the two electrons. And L, M, N, these powers are integers. I think they have to be negative for some of these coefficients to work. Hyrias, back in the late 20s, I believe working with Max Born in a desk calculator, did like the first 38 terms and got the ground state energy to negative 2.9037. Over the years, it's been improved. Pekaris, 59, one of the earliest, maybe the earliest, done with an electronic computer. He got it a little further, about 10 digits. Now, fairly recent result, 2008, Nakasuji, it's up to about 40 digits right now. So, approximation techniques have let us calculate the ground state energy to a reasonable accuracy. The experimental value is 2.903, and right here on the fifth digit here, that's where it kind of goes off the rails. Probably it's due to the assumption that the nucleus has infinite mass. We ignored nuclear motion here. The electrons go to one side, the neutron, will go to the other way. Helium, let's see, I think a proton is 1,800 times more massive than an electron. So helium-4, 2 neutrons, 2 protons, probably 7,000 times more massive than the electrons. So yeah, about 1 in 7,000, that's about where this thing just kind of goes off the rails. And just knowing just kind of what the numbers are, that's probably the effect that you first see that causes this to deviate from experiment. It's the neglect of the finite mass of the nucleus.
Plausible.
Yeah, and then, so it's one sense, past that fourth digit is just kind of a pure mathematical exercise, but that's okay. This is the math department. We just have an equation we're trying to solve. It's an approximation. It's only accurate to about 4 or 5 digits, but that's okay because if we can learn to solve this equation, maybe we could solve more complicated ones, right? Okay, so most people that have attempted this, come up with more various series expansions, and you truncate 1,000 terms or something, and shove it all in a computer and try to adjust your parameters to minimize your ground state energy. I've been going at it for years from a different angle, and that is differential algebra. That's just my preferred attack route on this problem. That's how I first got involved with this seminar. I met Sasha at a differential algebra conference a little over 10 years ago. That's how I got into the Riesz equation. That's all differential algebra. Robert Riesch's work, the stuff I lectured on last year. That's how I got into study the integral, beat it to death, and maybe learn from that how to attack a more complicated PDE. Hasn't quite panned out. I don't think the integral techniques generalize quite the way they do in the analytic case, but that's why I'm interested in stuff like the Riesz algorithm. It's really to attack PDEs more so than trying to pick apart integrals. So okay, so what can we pull from differential algebra that might be useful for this this application? Picard-Bessio theory, based back 100 years or so. Good reference on this that I like, Van der Put and Singer, Galois theory of linear differential equations. One of the things I like about it is one line. You can just get the PDF of the whole thing. They have a nice, nice presentation. That's their first chapter.
Singer's first name is?
Michael Singer. He's emeritus at NC State, I believe. So we want to do a matrix formulation. I mean, it's just start with just the ODE. Picard-Bessio. Well, let's start with the ODE case, and we'll get to the PDE in a second. We want to do a here's second order PDE. So we have a differential operator on a vector, which is just y in its first derivative. So of course we have y in the second derivative, and then I can set this up. So the first derivative is just the first derivative that way, and then the second derivative gives me my actual equation. Here's the same setup with a third order inhomogeneous equation. I can just also throw a constant in there and just say it's all zero. Its derivative is zero, so it's constant. That's how I can mix a 1 in there. At least there's a multiple of some constant. And there's my y differentiates to y tick differentiates to y double tick differentiates to y triple tick, which is my equation laid out here in the third.
In the example above, is your first equation missing a y prime?
Where am I missing a y prime? No, in the equation itself?
No, up at the top, yeah.
In the equation?
Right.
No, there's no y prime there.
Well, you say y double prime equals zy plus 5/16 c to the minus 2 y prime.
Yep. It's a first order differential operator.
And I'm not talking about that, I'm talking about the equation above.
Yeah. Yeah.
How come
Second derivative equals this multiple of the function itself.
Right, but down below, looks like you're saying is y double prime equals zy plus 5/16 c to the minus 2 times y prime.
Oh yes, you're right. This should be collapsed into
Z plus, and then a 0 over in the first spot.
What's that? Yes.
0 over in the right hand.
Yes, 0 in the right hand
Okay,
spot.
all right. The equation is correct. The matrix is wrong.
Yeah, I did the matrix wrong. You're right. Good. Tells me you're paying attention. I deliberately put that in there just to see if anyone would catch it. If you believe that. Okay, so
I've
that's...
seen the trick before, so I believed it.
Right. Okay, so we have a matrix formulation. Some y is some vector now. Its derivative is some matrix A times y. A is some n by n matrix in a differential field K. So we have this little lemma that if the solution vectors are linearly dependent over the differential field K, then they're also linearly dependent over the constant subfield C. And what that really leads to is this, that the matrix equation has a solution space, it's a vector space over C. It's kind of obviously a vector space over K because it's a matrix over K. But it's also it's a vector space over the constant C of maximum dimension n. And in one sense, you think, well, let's see if it means that there's a second order ODE. So it's a 2 by 2, homogeneous 2 by 2 matrix. So n is 2. That means we're going to have at most 2 linearly independent solutions of our ODE. I mean, kind of makes sense. It is an inequality at this point Yeah, maximum dimension n, and yeah, I didn't really just put it. Look at maybe in the next slide we'll have a less than or equal to. No, okay. It can be less than. It can be a strict inequality, and the reason is because the assumption here is that everything is in K. Both the matrix and the elements of the vector y are all in the same differential field K. So like coming back to this example here, my matrix for my matrix here M, the K is just the rational functions in Z, right? I can make K small, and no, I'm not going to have any solutions to this equation in just rational functions in Z. I'm going to at least need some kind of exponential there to solve that equation. So if I make K small, I can have less than n equations. Kind of the point of the lemma is that if I make K big, I'm not going to have any more than n solutions. And then, well, let me just, how did I word this? If there's exactly n solutions, we can form an n by n matrix of the solutions, called a fundamental matrix for the equation that says B and A are both n by n matrices. B is just the solutions laid out in columns. And then the question is, if we don't have n solutions, can we extend the field to get n solutions? And the answer is yes. It's really, I've come to see it as very much analogous to, it's differential, it's Galois theory. It's different, it's like you're extending to get an algebraic extension. If you have a polynomial that's irreducible, you can just adjoin an element and make it reducible. You might have a problem if you're in characteristic P. You might deal with separability issues, but certainly in characteristic 0, you can just adjoin an element and just declare that element is a root of the polynomial, and now you've extended, and you keep this up, you get a splitting field for the polynomial, and now you can factor your polynomial. It's the same kind of thing here. A Picard-Vecchio ring is an extension of the field that gives you n solutions. So you can start with a field that doesn't have enough solutions, say rational functions in Z, and then you can always extend out. And if you look at the proof in the Singer and Vanderput book, it's just like it's just the kind of adjoining elements. You just need to adjoin more than one element. If it's an n by n matrix, you need to join n squared elements maybe. But you're just adjoining elements, and you can build this bigger field. It is not a constructive procedure, but there's an existence proof. You can build a bigger field that gives you n solutions to your equation. And then just the standard Galois theory now, we've extended to this, larger field. What happens when we start, we form automorphisms of the larger field that fix the base field, just like we do in the algebraic case. And what the differential Galois theory tells us is that for an n-degree matrix equation, we have a differential Galois group that is a subgroup of the general linear group of degree n on your constant subfield. Yeah, it's just a Lie group. You figure with algebraic equations, your Galois group is it's a finite group. This time, this is an infinite group. It's just, if it's a linear ODE or a linear matrix equation in general, it's going to be a subgroup of your general linear group, which is, in one sense, kind of convenient. And then a Liouvillean extension of a differential field is a series of field extensions that are one of three. Each one is one of three cases. Either it's an integral. We start with the base field and extend by one element each time. It's either an integral, or it's an exponential of an integral, or it's algebraic. And it's a little bit more general than an elementary. It's kind of like the same construction with an elementary form, except that these can just be arbitrary integrals. The integral does not have to have an elementary form. We're just asking now is basically, can we extend by first order ODEs to build a solution to our nth order ODE. Okay? And then there's a couple, I threw this in here, this Vanderput and Singer reference, mainly just because this connects to the next theorem, and that is to say if one of these Picard-Messier extensions is also a Liouvillean extension, which is to say if you can write your solutions using a series of integrals and exponentials and algebraic extensions, then the key fact is that the connected component of identity of your Galois group is solvable in the sense that the derived series of its commutator subgroups eventually stabilizes to the trivial group. So you just construct all your commutator subgroups and it eventually stabilizes. And then Michael Singer, back in the early 80s, proved this theorem, and that is that if that all happens, then your extension is at worst this. N extensions, 1, 2, 3, 4, 5, up to n, where n is the size of your matrix. The first one is algebraic, and all the remaining ones are either exponential or integrals of exponential. And the point is, we're starting to make a little bit of progress into characterizing, if you're trying to solve an ODE, in this case, an nth degree ODE, there is a limit on how many extensions you need in order to do that if it's a Liouvillean. If you can do it with integrals and roots and exponentials, then you can do it in, at most, n steps. You don't need any more than n steps. First step's algebraic, and remaining steps are either integrals or exponents of integrals. Okay, so here's an example. Jerry Kovacic's algorithm. Jerry Kovacic published an algorithm back in around 1980 that solves linear second-order ODEs in much the way that the Riesz algorithm solves integrals. It can either determine that there's a closed-form expression or prove that no such expression exists. And how does he do it? Well, he breaks it down into four cases. The fourth one is there is no Liouvillean solution. And then the first three cases are the solution is the exponential of an integral, or the solution is the exponential of an integral that's algebraic, or the solutions are in fact algebraic. And that ties back into Singer's theorem. What does Singer's theorem tell us? Well, this is a second-order ODE. Okay, so if it has Liouvillean solutions, it's going to be, at worst, an algebraic extension followed by either an integral or the exponential of an integral, and that's it. And that's exactly the three cases that Kovacic identified. It's algebraic, or it's the exponential of an integral, or it's algebraic followed by an exponential of an integral. And that's it. That limit, that's just the limit on how complicated the extensions need to be to solve a second-order ODE. Okay? So how do I, what is the relation to this to what I'm trying to do with helium? Well, how would we set this up for a PDE? Okay, so we set like a heat equation. We can set up a matrix formulation where we have our partials now with respect to like two variables, x and t. And we can do a matrix formulation, but the problem here is we don't know what all the elements in the matrix are. If it was a total differential equation, if we knew what all of our partial derivatives were, then we could set up the whole matrix. We don't know that. We only know what some of our partials are. Like we don't know what the partial with respect to x is. So we have second derivative with respect to x, we have first derivative with respect to t. There's nothing in that equation that tells us what the first derivative with respect to x is. So that row in the matrix is just a bunch of question marks. So then, I started asking myself, okay, so what does like the Singer theorem tell us about all this? Well, it's still a matrix formulation, so we need some kind of mystery extension in order to fill in these question marks in the matrix. You know, we don't know, I don't have any theory that can tell us what extension we need to fill in the question marks in the matrix. Once we fill in the question marks in the matrix, then Singer's theory tells us that after that, if it's 3 by 3 matrix, we need an algebraic, maybe, followed by 2 more extensions, integral and exponential of integral. Okay, so this is an example of the heat equation. I'm just going to skip that and go to this. Do our known hydrogen solutions fit into this framework? You know, if we write out all of these different partial derivatives and look at how it would work in a matrix formulation, we don't know what a lot of the rows are in this matrix, but we know what some of them are, and then so what we need some mystery extension to fill in the rows of this matrix, followed by an algebraic extension, and it looks like up to 5 integrals or exponentials. So do the known solutions to hydrogen fit into this framework? And the answer is yes. The mystery extension is trivial. The algebraic extension is trivial, and we need one of the possibly 5 integral or exponential extensions. We need one. We need an exponential. All of these have the same form. They all have a algebraic function in the field that we use to define the equation and a single exponential extension. Okay, so now I start thinking, well, I want to form an ansatz for helium along these lines. I'm not going to do the thing where I just come up with a whole bunch of series of functions. I'm trying to get them to all to converge. What I'm going to try to do is I'm going to come up with this kind of an ansatz. Okay, so I'm going to start with my field of definition, which is function field over the reals. Right? X, Y, Z, the first electron, X, Y, Z, the second electron. I already need to do an algebraic extension to get my radial terms, R1, R2, R1, 2. And then let's just assume that we don't need any additional algebraic extensions, because that was the case with hydrogen. And then maybe we need a first order ODE extension. I mean, that's what we needed with hydrogen. There's actually some numerical evidence, just simulation of the wave function, that looks like its singularity near the origin is proportional to an exponential integral. So maybe we need a second order ODE. So I'm thinking now I want my my helium ansatz to be something like a polynomial in this field, times an exponential of a polynomial in this field, and I'm going to put a degree bound on it and say it's either a first degree polynomial or a second degree polynomial. So if I look at all the different, say first degree in X, Y, Z, arbitrary degree in R, I would get a polynomial with 56 coefficients. Take one of those polynomials times an exponential of one of those polynomials, add the energy E, you get 113 coefficients.
Can you give us a little? 10 seems reasonable. You have 9 variables up there, and I suppose
right.
one for the constant term.
Yeah.
How you're saying 62 and then 56?
Yeah. Okay, so 56.
How do you get 62 and how do you get 56?
Okay, so 56. I'm going to allow arbitrary degree in R. So I'm going to allow R1, R2, R12, R1 times R2,
okay.
R2 times R12.
So all those.
Yeah, there's just 8 of them. There's 8 possibilities
right.
there. And then there's, constant. And then there's X and Y and Z. I'm going to multiply each, 8 times 8 times 8. So I'm going to get, and there's 6 XYZs. Because there's one for one electron and one for the other electron. So there's 6 of them, and I also have a constant that I'm going to throw in there. So it's going to be 7 times 8, which is 56. That's how I get 56. Okay? And then I'm going to say, I'm going to take one of those polynomials times exponential of one of those polynomials. That gets me to 112. And I also need my energy, which I don't know. That gives me to 113. I plug that into Schrodinger's equation. I cancel everything out. I get 993,000 equations, 993,262 equations. And that's after removing duplicates. So they're all polynomials. So I got like a big system of polynomial equations.
What order of polynomials?
3rd degree at most.
Even so you can't calculate that sort of thing.
There's no, so you can't plug, first degree, you can plug it into a matrix thing, but yeah. So we got,
each one would probably be doable, but not a million of them.
well, that's what I'm trying to do. That's now I'm getting to, you know.
This is the first
it's time for a
non-trivial step?
What's that?
This is the first sort of, this is like the first non-trivial step where you want to calculate it?
I would say so. I'd say up to this point, it's pretty, propose a trial polynomial, plug it into a differential equation, expand it out, collect your coefficients.
And your goal is to apply this to helium.
Yes.
And get a bit, and get something that's closer to the number that's measured.
I'm trying to get an exact solution. I'm trying to see if I can solve these equations exactly.
What about the nucleus and stuff? You gave an argument that
okay.
That's not included in this, right?
That's true. I'm treating it as a pure math problem right now. Can I just solve this equation and find a closed form solution along the lines that the differential algebra analysis suggests? You know, a first or second order ODE and just, you know, algebraic polynomials. Okay? Mm-hmm. And that leads me to, okay, how do I then actually solve an equation, you know, a system of equations of this size? And that's the challenge that I'm trying to tackle right now.
What about the error for hydrogen? Presumably, there's an approximation also due to the nucleus, which is a proton, and then whatever that error is, how does it change when you move to deuterium and tritium?
What they typically do with hydrogen is they use a reduced mass. So you don't have to really take the nuclear
why not?
Movement into
there
it.
There should be some slight discrepancy if there's a nuclear effect.
Well, what, you mean a nuclear mass effect?
Yeah.
I think if I haven't sat down like written it all out, but I believe if you use the reduced mass for, you know, the electron, that you do get an exact. It takes the mass of the nucleus into account.
Really. I don't know. Maybe somebody here does. You take the prediction for hydrogen.
And try to include the mass of the nucleus?
Yes.
Well, you're going to have another variable, you know, for the mass.
But, I mean, there's a prediction from what Brent was talking about, which will give you a number for hydrogen, which I know is very close to the observation. But I'm assuming that they're not exactly equal, and wondering if that discrepancy has been studied, and if
I imagine it has.
And
it
how
could
does
be
it
data
figure?
relativistic stuff too.
That's what I see. That's what I think. I believe that just using the reduced mass for the electron instead of the actual mass for the electron takes that effect into account, and the discrepancies in the hydrogen solution are due to relativity and magnetic effects. Okay. All right. So it's break time. Let's take our coffee break, and when we come back, then I will tell you how I'm trying to solve this huge system of equations. You know, huge number of equations and 113 unknowns. How do we deal with them? First of all, it's an algebraic variety. That's you know, the exponential just drops away. I mean, I guess you could try and deal with the exponential. I just collect all like coefficients of the exponential and just set the coefficients equal to 0, and what I get are a whole bunch of polynomials. And that's a significant fact. It's an algebraic variety. Certainly, it's not just any old, you know, collection of a million equations. So if you're trying to solve like an algebraic variety, what do you expect? Here's a simple system of polynomial equations where the solutions are, z could be 0, or both x and y could be 1 to solve these equations. So what we would get here is the entire xy plane and a vertical line puncturing through it at 1, 1. So this is a union of two irreducible varieties, the plane and the line. In this case, they're not equidimensional. They don't have, one's two-dimensional, one's one-dimensional. And one way to look at trying to solve an algebraic variety is to break it down into its irreducible components. Let's see what's next. Forget what the next page is. Let's see what the next page is. Yes. So seeking primary decomposition of this defining ideal. So it's just the standard algebraic geometry duality that developed in the 20th century. A variety is a set of points that solve a system of equations in geometric space. The corresponding algebraic concept is a radical ideal. Why is it a radical? Well, the solutions of y to the fourth equals 0 are the same as the solutions of y equals 0, assuming that our coordinates are taken from a field. We have no nilpotence, so really it's the radical of an ideal. The radical being all the polynomials that some power is in the original ideal. In this case, you have the radical of the ideal generated by y to the fourth is just the ideal generated by y. So varieties in geometric space correspond to the zeros of ideals in the algebraic space. An irreducible variety corresponds to a prime ideal. A union of varieties is dual to the intersection of ideals. So if I have a variety, and I know what its equations are, has a defining ideal, and I want to decompose the variety into irreducible components, algebraically, what I'm looking to do is a primary decomposition of the ideal. Primary decomposition meaning the ideal can be, any ideal can be represented as the intersection of a set of primary ideals. And then if the primary ideals have associated prime ideals, and if the original ideal is radical, all of the primary ideals are prime ideals. So it's, I guess it's something you probably find in a graduate class in commutative algebra. I mean, just kind of blew through it in 30 seconds or something. But basically, we want to decompose a variety into its irreducible components. What we like to do algebraically is take the ideal and find its primary decomposition, and if it's radical, we expect that what it's going to be, it's going to be able to express the ideal as an intersection of prime ideals. Each of those prime ideals is going to correspond to one of the irreducible varieties in the geometric picture. So
you have to work with a million.
Right. So we just fire up Sage. Here we go. So we have this is the ideal for example: x times z, y times z, right? That was the example I had. Actually, I had I made it a little more complicated. X minus 1. It was x minus. Okay, this one I guess is a little different. It's x0, y0, and you call associated primes on it, and you get it breaks you down. There's your two irreducible components, and the one ideal part. This is the xy plane. And this is the line, x equals 0, y equals 0. Set the equations, set the polynomial is equal to 0, that defines, it uses like Gröbner basis type techniques under the hood. Try it on even hydrogen, and I let this thing run for a while. I was hoping to have like a timing on the thing. Let's take a quick look and see if it's done. Nope, still running. I started around noontime. And that is not helium. That is the hydrogen ansatz expanded out, and you get all these equations, and you just tell it to.
Mistake on line 14.
Yeah. Not my mistake. It's the computer's mistake. Maybe a bit got flipped somewhere.
Of course,
Yeah.
English words.
Yeah, but this starts to have. Principle, just call associated primes but it has computational difficulties. I mean, of course it has, we're going to have problems with this calculation. There's just so many equations. So in principle, you can just feed the thing into stage and call associated primes on it, and it'll give you a decomposition of the thing into a nice set of irreducible components. Certainly something useful to know if you're working with a relatively small variety, but it just doesn't scale in this case. You see, I mentioned Rosenfeld-Gröbner because I feel like I should mention it. It's kind of going in the wrong direction in the sense of complexity. Rosenfeld-Gröbner is a generalization of the Gröbner basis algorithm. It computes prime decompositions for radical differential ideals. So a Rosenfeld-Gröbner calculation, you can set it up like this. In addition to just polynomials, you can have derivatives of polynomials. It's a differential ring. You have your polynomials, you have differentials for your polynomials, and you can plug that into Rosenfeld-Gröbner. It has trouble even getting to, it can do a simple calculation. These are hydrogen ansatzes. As soon as it gets to like a radial term in the polynomial that you're multiplying by the exponential, it really starts to slow down to a crawl. And that's not unexpected because it's a differential Gröbner basis calculation. It's even more complicated than a standard Gröbner basis calculation because it can handle differential ideals. So this is going in the wrong direction in terms of complexity. But I just...
You don't tell Sasha.
Oh, is he doing something with Rosenfeld-Gröbner? Do you know?
What?
Is he doing anything with Rosenfeld-Gröbner? I know he's doing something with differential
I
algebra.
imagine so, but he's not doing computer work.
Yeah.
Is that Moshe Rosenfeld, the guy who was at University of Maryland?
I do not know. Francois Bollier, who's a French professor, he has done a lot of work with this. I don't know why they called it Rosenfeld-Gröbner. And Bollier is the primary author that I associate with this.
Named Rosenfeld, he wasn't working in this area that I knew of.
Mm-hmm.
It does use, it's related to computers, and he was in computers.
Okay. I don't know. Okay, so here is a different approach to decomposing a variety, and this is the approach it's making, I feel, better progress than something like a Gröbner basis calculation. So let's say we have this equation here. We're given, I don't know, x, just some polynomial here. And if you were to, you could factor the thing. This is an easy example. What it is, it's a straight line and the unit circle. Okay? That's what this polynomial, that's what its zeros are. So let's say, how about this? Let us pick a...
You mean you want something that satisfies both those equations, so it's really the 2 points where they intersect?
No, I'm
So I thought a variety was the locus of points x, y, z, or whatever space that satisfy a particular equation.
That's right.
Okay.
So the locus of points that satisfy this equation are this line and this circle.
So it's a union.
It is a union.
Okay.
It is a reducible, right? It can be you could just factor this polynomial. It's just a toy example.
I see either term could be this.
Yeah, it's a toy example. When I'm I'm proposing a way of doing it. I know you could just factor it, but this is a way that generalizes more into the million equation environment. Okay. Here's how I suggest doing this. Let's just pick a point at random. It's not going to satisfy this equation, but when we plug in these coordinates, it's going to give us something that is not 0. And let's say we now run just an optimization, gradient descent, something like that, and we just start stepping the thing numerically until we get to a point like this that's within some epsilon of our variety. So here is 0.7631 and 0.6457. We would plug them into this F, and we get something that's spelled 0.001. So it's getting close to 0. It's within some epsilon of 0. Okay, and then I look at my x, my y. They look just like real numbers I just kind of pulled out of a hat. But if I take their squares, and add them, I get 0.9992, which is almost 1. And the point here is that the coordinates of the points, because it's on an algebraic variety, the coordinates satisfy some kind of an algebraic relationship. And that even an approximate relationship, is discernible. You can discern this as approximately 1. And we have an algorithm, the number of these, but I think this is the most well known, the lattice basis reduction algorithm, Lenstra-Lobot's, which is given a basis for a lattice in integer n-dimensional space, computes a reduced basis for the lattice, and the lattice is everything that's generated, a bunch of coordinates with integer coordinates. The lattice is everything that's just generated by those points under addition, just pointwise coordinate addition. It's a polynomial time algorithm, and what you get is this reduced basis where the length of your shortest element is less than twice the length of your actual shortest element. Actually finding the shortest element in a basis is NP hard. But what this thing does is it lets you get reasonably close. We got a tight bound that is within twice the actual shortest length, and it runs in polynomial time. How can it be used in our problem here? Well, we just take our values, our x, our y, our x squared, x times y, all of our first and second order coefficients. Let's just multiply them by 1,000 and round off to integers, and then slot them into a, what's this going to be, a 7-dimensional integer lattice. These are the basis vectors of our integer lattice. Run it through our lattice reduction algorithm, and what do we get? Well, if we took element B3, which is the x squared, B4, and subtracted B6, which is 10,001, we would get the x squared plus the y squared minus 1. It's going to be negative 8, approximately 1, and then 1, 1, negative 1. And these other columns, well, just the Euclidean norm of this thing is 8.185, which is a heck of a lot less than all these other ones, which are up in the thousands. So
when you divide by 1,000 or 10,000 or what?
I multiplied everything through by 1,000. I took my approximate real coordinates from the last page.
Didn't you multiply by 10,000, I think?
I guess I did. Yes, I multiplied by 10,000. Yes, you're right. I multiplied by 10,000. You're right. Yes, I multiplied all these by 10,000. Rounded all, just truncated them, rounded them off to integers, and I have a polynomial time algorithm that will identify for me candidates. I mean, I can just read off here. It's x squared plus y squared equals 1. I can jump from an approximate solution to an exact solution. So, in the numerical algebraic geometry literature, one of these approximate solutions like this is called a witness point. It's a witness to the irreducible component that it is almost 1. And if you can compute the witness point to a high enough precision, then we've got an algorithm with the lattice basis reduction that lets us jump from that to an exact solution. We go from an approximate solution to an exact solution. And that is the basic idea that I'm pursuing, is to try to solve this large system of equations. Attack it as an approximation problem and figure if I can get a good enough approximate solution, then a lattice basis reduction should let me jump from that to an exact polynomial solution. All right? So what, okay, so implement, how do I implement it? I'm doing it with Sage. I have access to a decent mini computer that's got, 96 processors, probably actually over 100 when I I got a couple more I could throw in there. Let's say about 100 processors, 768 gigabytes of RAM. So I have a decent machine at my disposal that, well, you got one too if you want to slap your credit card down for Amazon's web service, but I've got one that I can just use for free because, my friend Bruce owns it. So I have access to, a reasonably powerful computer. So I want to implement this in Sage, and I want to do it in parallel. This is, I got some, the last page in this handout are some complexity estimates that are a little bit sobering. But hopefully with 100 processors, all running in parallel, it might become tractable. So how then do we do this? Basically, you have two rough ways of doing multiprocessing on a computer: threading and multiprocessing. Threads, you have multiple processors running simultaneously in shared memory space. Processes, you have multiple processors running in distinct memory spaces. Threading is more efficient generally because you don't need as much memory because they all share the same memory space. You don't need to duplicate stuff. But it does require all of your objects to be locked. Like if I want to access a particular list, if I want to update the list, the thread has to lock it, update it, and then unlock it to prevent other threads from coming in and trying to, if two threads are simultaneously trying to modify the thing and they're in shared memory, it's a problem. So Python deals with this by having a global interpreter lock that just prevents more than one thread from running Python code simultaneously, which is a little bit of a problem, not a huge one. It just means that threading is not an effective technique in a Python program for parallel computation. Threading is useful for control operations. Like I called a subroutine, I want to start something running in background and return back to the main program. That's fine. Actually getting a dozen processors to do something in parallel, no, it's just going to run like it's one processor, because they're going to be constantly stopping to wait for each other in the Python code. So for Python, multiprocessing using multiple processes is the preferred technique. And one of the nice things about Sage is that it's built on Python, so you got these kinds of tools. Python has a multiprocessing library that the Sage guys didn't have to write because someone else wrote it for Python. You got a lot of stuff written for Python. You can use it all. And you got NumPy, you got SciPy, you got the multiprocessing library, all of Sage's symbolic capabilities, just all kind of pulled together in one system. So let's see here. This is just a diagram that shows, okay, if I were to take just the Schrodinger equation, the Helium-Onslaughts, plug it into the equation and type expand at Sage, it runs out of memory. And the reason it runs out of memory is because this is like the first term in the Helium expansion. This is what the first term looks like. And the way it's stored in Sage is this kind of a tree, where I have a bunch of things multiplied together, and then this one is a power, and this is a sum, and it's a sum of powers, and it's x1 minus x2 squared, y1, y2 squared, z1, z2 squared, summed up. And each one of these things takes, I think I figured, 72 bytes. So this whole structure takes about almost 4 kilobytes. It's just not, I can actually fit this one in memory, but once I really start to expand these things out, when I expand out all this cube and all this stuff expands out so I can collect my terms together, it just runs out of memory. So this isn't too useful. So this is what I do. I have a bunch of processes working to expand 1,000 terms at a time. Just takes 1,000 terms, expands them out, and then slots them into a big sparse matrix where the rows in the matrix are the factors that I want to collect on, the x1, x2, z1, and the columns in the matrix are the coefficients that I'm trying to solve for. So I have, it's like, R1, R2, X1 to the 8th, X2 to the 4th, Z1 to the 5th, that's the row. The particular coefficient is negative 1304, A31, B13, B14. It goes boom in that slot in the matrix. It's a sparse matrix formulation. It's really based on the fact that it's third degree at worst in these coefficients, so I can just slot it all into a sparse matrix. And then there's a bunch of processes that are running in parallel to expand out, all these terms, and then I got another bunch of processes that are running in parallel that store the rows of the matrix. So what I end up, it takes about 2.5 hours to expand out the basic helium ansatz. I get a sparse matrix at about 1% density, and it's spread out over a dozen processes. Okay, so a little bit here. I'm just going to accelerate, so I'm getting towards the end of my time. A little bit here about how SciPy stores sparse matrices. Basically, it has a dictionary of keys where it has like a hash table. It points the key to a number, the value in that particular entry in the matrix that's relatively fast for accessing individual elements. And then it has this compressed sparse row format where it stores the whole thing, the non-zero entries, in row major order. And the dictionary of keys format is convenient for building the matrix. Compressed sparse row format is convenient for operating on the matrix, doing like a matrix multiplication, for example. So what you do is you build it, and this, just if you read the literature, it's the recommended approach. Build the sparse matrix in one format, dictionary of keys. Then once it's run for 2.5 hours, expanded everything out, then convert it to the sparse row format, and now you can do various matrix multiplications. So how do you how do you, for example, evaluate all the polynomials at a specific point? We send a vector of 113 floating point values out to the thing. This gets sent out to all the worker processes, and then we do this kind of thing. We have our ABC, so we have 3 values. ABC, and now I'm going to take that and multiply them by A, get A squared, AB, AC, take these two multiplied by B, take this one multiplied by C, and that gives me all of my byproducts, if you will, my 2-factor products. And then I do the same thing for my tri-values. Take all of these things and multiply by A, boom, 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 boom. Then take this set here, multiply by B, and then take the final one and multiply by C, and that gives me all my tri-values. And if it's selection with replacement, so I have 113 values, 114 choose 2 byproducts, 115 choose 3 tri-products. It gives me a vector of 253,000 elements. That gives me all of my my products, and then I want to multiply that vector by the sparse matrix. And there's a similar trick that I can use with these vectors to figure out what their partial derivatives are. And then ABC, my partial derivative, and I can do something similar with the byproducts and add them up, and I get a vector of that I need to multiply by if I want to take the partial with respect to A or the partial with respect to B. And then I can call the SciPy sparse matrix multiplication code, which goes into this tight little C loop here and does a sparse matrix multiply. And if you take a look at this code, it's it can be optimized a bit. It doesn't. I've talked about how modern processor has superscalar instructions. It does like multiplies in parallel. This code doesn't multiply in parallel particularly well. So I think this could be tuned a bit to like take pairs of floating point values or quadruples of floating point values and do like 2 in parallel and 4 in parallel. So that's just one of the kind of to-do items on the list here, is to go in here and fiddle the code a bit to work better on a modern processor. So, okay, 620. How much more I want to go? We just mentioned, what are our Intel floating point options here, just in case you know, doing any kind of work like this. Basically, your hardware options are, you got 32-bit floats, 64-bit floats, and 80-bit floats. The single precision 32-bit and the double precision 64-bit have been vectorized. The 80-bit has never been vectorized. So for your SSE instruction set that was introduced around 1999, you have 128-bit wide arithmetic logic units, so they can do 2 double operations simultaneously or 4 single point operations simultaneously. AVX, which was introduced I think in 2013, is twice as wide. It can do 4 doubles or 8 singles simultaneously. And it cannot vector. I mean, 80 bits, that's the largest the Intel supports. They can't be vectorized. You just do them one at a time. And then the very newest thing is the AVX 512, which is 512 bytes long, and that lets you do 8 doubles simultaneously or 16 singles simultaneously. And then, once you say that you want more resolution than that, there are software floating point libraries. Those are just your options if you want hardware support. You can also do the calculations in software. It's a little bit tricky because, well, no, it's not tricky. It's just inefficient the way it's currently done in Sage. It can be done. Here's an example of a Sage calculation where I create a 128-bit field. So this is a floating point number with 128 bits of resolution. We don't have any hardware floating point for that. Our highest is 80 bits. So this is all done in software. And I can do an array from 1 to 9. I can do an array operation. I can multiply this all, 128-bit resolution floating point stuff. If there's a problem here, it's just that it's not stored particularly effectively. It's that each of these values is stored in a Python object. You see that's why the data type is object. It's done with pointers. There's garbage collection. There's a lot of overhead here in terms of memory and compute. Certainly for a small matrix, it's fine. If you want to do high precision floating point stuff, you can certainly do it in Sage. And if your matrices are relatively small, everything is going to go fine. It's when you get into the size of things that I'm dealing with that it becomes a bit of an issue. All right, let me just and numerical recipes. Interesting. I'm running out of time. Suffice it to say that these are 2 good references on numerical techniques. The most obvious way to do this would be to take the sum of the squares of all these functions and treat it as a minimization problem. That turns out to not work so well because you get a lot of local minima that disrupt that process. If, on the other hand, let's just say that we had the same number of equations as variables. If our Jacobian matrix was square and the linear approximation was exact because the Jacobian is first derivatives, then we would want to solve this equation. After the values of our functions, say 100 of them, at some particular point, j is the 100 by 100 Jacobian. If we were to solve this and the linear approximation was exact, then this delta x would give us the change in the 100 coordinates we would need to just zero out all these functions. The numerical recipes book recommends doing an LU decomposition if the matrix is, first of all, just for solving it, and also if the matrix is large and rectangular. And what I've done is I've implemented a parallel LU decomposition that computes, copies these matrices out on a whole bunch of different processes. Each has a block of rows. Each one computes the Jacobians for its particular block of rows, And then the main process, tells each of these little worker processes, go and pick your candidate for the best row to pivot to the top at each step. It picks the one, pivots it to the top. They all search in parallel for the next one, pivot it to the top, search in parallel for the next one, pivot it to the top. And what you end up with at the end is most of the processing is done in parallel. The main process has this top little, LU decomposition with the rest of the L matrix spread out in all these processes. So you then just discard this information. You never have to copy it back to the main program. You just discard it, solve this thing for your delta x vector, and that gives you the next step in your decomposition. If you were to just call, this is done in NumPy. They have a subroutine that can do this. The problem is the subroutine expects to be given a function that just computes the entire Jacobian matrix and gives it to you. This way, it's done in parallel. The Jacobian matrix is never collected in one spot, and just the main process, all it does is it pulls back from all of its worker processes just the top part of the matrix, and that's just the part it needs to do the to compute the direction to move in for the next step of the approximation. And I've done some complexity estimates on how long I think all this would take if I cranked up the floating point resolution to 1,000 bits, which is I kind of think where I might need to be to do a lattice decomposition with 100 variables. I would think that I think probably need at least as many bits as variables. It's just a gut feel. Could I really do a lattice decomposition on 100 variables if I had only computed them to 64 bits? I don't know. But let's just say I need a 100-bit resolution and run the whole thing, and I conclude that doing the floating point calculation with software would take about 3 days on 100 processors in parallel. Actually 4 days. 3 days to compute the Jacobian, another 20 hours to execute the parallel LU decomposition. So each step in the iteration would take about 4 days. So I don't know. I think if I get a good enough candidate at lower resolution, you might look at the energy level, see if it's starting to get close to the known approximate value of helium, that we know to 40 decimal places, then I might be able to crank this up to higher resolution, let it run for a couple months at this rate, and see if it can find an exact, see if it can get an accurate enough witness point to find an exact solution. So that's the strategy for how I'm trying to proceed. Okay?
Were you talking about the ground state of helium?
Yes.
It's known, and you would see if you could come up with a good approximation to it.
Well, I would say we have we have approximations to it, and I'm trying to find something.
Yeah.
Yeah, we know it's ground state energy to 40 decimal places. So I'm saying running this at low resolution, 64 bits, see if it's close enough to that negative 2.7 whatever number to justify running it at this resolution and this speed to see if it can get to an exact solution.
Wow.
So you don't feel any need to kind of the way Michael showed me it's a program, which always seemed very efficient, was to start with a simple problem, get something that works, where you can check it, and then gradually make it more difficult, add things that you want to do, but always you have something that's working. Here, you're saying, well, if it gives me an answer and the answer looks close enough to something plausible, then it must be doing the right thing. That might be risky because one has so many ways, unconsciously, of getting things to come out. I've done it many times, where the numbers came out really well. Oh, this must be right. But somehow, like talking Hans, I was cueing myself and I was getting the right answer, but not necessarily for the right reasons.
I assume that Brent does toy versions first.
The toy version is hydrogen.
Yeah.
I mean, I can run hydrogen on the laptop right now if you'd like to see it.
It's going to take 85 hours.
It's going to take 85 hours. I'm going to call this, I'm going to say prep hydrogen instead of prep helium. I'm going to multi-init, which fires up two processes. Yeah, it's going to fire up two processes because it's multi. It's a test on the laptop. There's two processes now. I'm going to do a multi.
So we'll be out of here.
Multi-expand. You know, just expanded them out.
Yeah.
Remove. There are duplicates. There, and now it goes and it finds all the duplicates and removes them. And then let's see. What do I want?
I'm willing to believe that it runs in a reasonable amount of time.
There.
It gets
Let's
right
just see. It's now running. So this is doing its parallel LU competition. It does have some problems with numerical stability because some of these, you think if you've got a pencil that goes up, one of these solutions, you just have a free variable, like a constant of integration. The something of e to the 93rd power is a valid witness point. So it has some problems with numerical stability, but you see now it's getting into, and it's done. Energy is around -1/8, which is the 2s, 2p, the second level of hydrogen. Most of our A coordinates are 0. A2 is huge. That's one you say. A2 is just free. It can be anything. B1, that's the exponent. It's -1/2. It's r over 2. If you remember what the, if you were to go back to the. If it's on the front page, it's r over 2. These are very small. This one's arbitrary. That's why it's huge. Yeah, this is one of the. That's probably the 2s solution to hydrogen. So yeah, I use hydrogen on the laptop, and hopefully once I get this running well.
And you ran that just now on this mini computer.
I'm running on this laptop right now.
Just on the laptop.
Yeah.
So with the mini computer, you got 100 times more power or something. What is your friend Bruce doing with that sort of a mini computer? Maybe I shouldn't ask.
Mostly it was intended for training. Like if we're teaching a class with 20 people in it. See, it used to be 20 years ago. If we're teaching a network class, we bring in 20 routers, and the student, boxes of 20 routers, and the students work on the 20 routers. Nowadays, it's all done in simulation. Nowadays, if you're teaching a class of 20 people, they have 20 simulated routers in a simulated network on a mini computer. I mean, it's a lot of computer networks, especially training and testing, has moved heavily into simulation in the last 20 years or so. And that's what Bruce bought the machine for, to teach classes, to teach networking classes, and be able to simulate networks. A powerful enough computer that could simulate a network suitable for training a room full of 20 people. Okay. Any other questions?
A couple other copies of this. I think you should need one for Sasha.
I got two more here.
Elizabeth could use one. She wrote a handbook on Python. I'm going to see her later tonight.
Sure. You give me this one.
Okay.
One for yourself, and I'll leave one for Sasha. Does he have a mailbox or something around here?
Sure, it's right on there.
Yeah. We'll leave it in Sasha's mailbox. Okay?
All right, let's thank the speaker.
All right.
Thank you, Doctor.